out that way, it would have worked any way I pulled it, but still the medium is going to move it in a transverse to the motion of the energy. Oh, where am I? Somehow I lost. Oh, how did I get down there? Weird. All right, longitudinal waves. Longitudinal waves. Now this is the way it moves in the same plane as the medium. Same plane as the medium. And it travels as a pressure wave. Pressure waves. These sound as pressure waves. So you have compressions, which are areas of high pressure, and that would correspond with the crest in a transverse or a surface wave. And you have rarefactions. Notice how we spell that. R-A-R-E-F-A-C-T-I-O-N-S. Rarefactions are the low pressure areas when it spreads out. That would correspond to the trough in our surface and transverse waves. All right? And so we have a series of compressions or rarefactions. These type of waves can go through any medium. They go through solids, liquids, and gases. And this is sound. And we know what it can do, because can sound go through a solid? Yeah, because you can put your ear on the table and if you tap the thing, you could hear it. You've all been probably underwater and heard sound underwater, so sound can travel through water. And it obviously travels through air. These are primary earthquake waves, the P waves. These are the faster, the first waves that get to the seismic stations. But they do go through the core of the earth. All that. S waves don't go through the outer core because the outer core is liquid. That's why we know the outer core is liquid, because there's no S waves on the other side of the earth. We know the P waves. We know the inner core is solid because of refraction. Basically, the P waves get bent, and so they change where they are and things like that. And so, anybody need more time on this page? I'll leave that. So, we come over here, and on my spring, and notice I'm going to put a compression in it. I compress it, and notice where the energy goes. The energy, you can see that energy going through the spring on that, and that compression. Sometimes if I get, you can kind of see see parts of it compressing and rarefacting. So notice how they're coming together on that. And this is how sound works. When I say sound, the sound there, sound makes compressions or rarefactions, and that's how it pushes against your ear. Chapter 26 will get more into depth in sound, like how your ears work and things like that. But notice at the end, does the medium return back to its original position? Yeah, even though I put the energy in there, after it goes through, it does return back to its original position. And that's what we mean by that it's the energy that moves, not the medium on that. Oh, were we good on that? So we have a couple of things here. So like this area and this area, those would be compressions. You'd have this area and that area would be our rarefactions. And basically a wavelength here from the beginning of that compression to the beginning of the next compression, that would be a wavelength. So just like with rarefaction are going to make a wavelength. So it's how many compressions go by, how many rarefactions go by, etc. Any questions about this? Surface waves are third type. Now this one is in the book, and I'm not quite sure why. I'm not sure why it's not in the book. The medium travels in a circle. The medium actually goes in a circle. Now the thing is, if you go to the ocean, you're watching ocean waves, which are surface waves. And you're out in the middle of the ocean, you would say, well, they look a lot like a transverse wave. And they do. If you just saw from a distance, you saw a surface wave and a transverse wave. They both seem a lot alike. It's like you get a crest, you get a trough, crest, and a trough, crest, and a trough. But it has to do with how the medium moves. In the transverse wave, the medium is going up and down, just a straight up and down. Here, it's actually going in a circle. It goes in a circle, and the waves roll along. In other words, the circle is like if you were in a cart, what direction would your wheels have to go forward? So whatever direction the wave is going, that's the direction of the circle on that. And these are ocean waves and surface earthquake waves. This is the wave that will destroy your house. And this is why people who are in earthquakes say, oh, it felt like being on the ocean. Well, yeah, because it's the same wave. And again, these will go through solids, liquids, and gases. I mean, there are waves like this in the atmosphere. There's waves obviously like this in the ocean. Earthquake waves, so it will go through a solid. So these all work away. And you can see these waves. These earthquake waves, they're big enough. You see them coming. The guy who I did my student teaching for way back when he first started, he taught at Anchorage High School when they had their earthquake in 1967, the 8-point-something earthquake. You know, he said he was at a restaurant. He had just stepped out of the restaurant. He actually saw the waves coming at him through the snow. You know, which was good that it was after school, because Anchorage High School was a 2-story high school. I think they rebuilt it as a 1-story high school, because like he had the chem lab was on the first floor, the typing room was on the second floor. When he went back after the earthquake, the typing room was in the chem lab. So I don't know what they've done since, but after that they did rebuild it initially as a 1-story high school. You know, there was a lot of damage. You ever see pictures of Anchorage? There was a lot of ground movement, like the whole downtown area, whole sections of downtown sank. Things like that, like 20, 30 feet of movement on that. You know, this is also pre-pipeline. And not too many people lived in Anchorage in those days. It's kind of a big city now. So if we look at this, notice it does look a lot like a transverse wave, doesn't it? In fact, we still use the same kind of terms. You know, we use, amplitude, we use wavelength, we have crest, we have trough. The difference being is that the water is going in a circle. If I put something right there, and as the wave go, it would go up, around, down, but it would end up back at the same spot. So if you're in the middle of the ocean, you don't move. The waves go by, you don't really move. If there's no current, which is a whole different thing. But if you're in an area that's no current, you would go up, you go down, you just stay kind of in the same place all the time. Now this is deep water, because there isn't just one circle here on this. If you were looking at this, and there's the surface of the water. Actually, let's... So we have a circle, a circle, a circle, a circle like that. But you have many circles going down. They get smaller and smaller as you go down. So it's all these little circles going down as the wave goes by. And depending how big the waves are depends on how deep this actually extends. I know in big storms, beyond submarine, guys were telling me in the submarine, so I was actually on a submarine in the summer, it wasn't that bad. But they said in the winter, they'd be like 200 feet underwater, and still the submarine's rocking because the storms on the surface were so large, you still were getting some of this even 200 feet underwater. They can't get much lower because they have to trail out communication cables out on the surface. So it kind of restricts them on that. Now, but this is in deep water. When you start getting toward the coast, though, well, again, you have you have the circles coming in and going down. But notice, eventually, what's going to happen to those little circles? They're going to meet with the what? The bottom, right? And they start touching the bottom. Well, you have moving water rubbing on the bottom. You're going to get what? Anything that rubs against something else, you create friction. So eventually what happens is these bottom parts start to, when you have friction, it's going to start to do what? slow down. So the bottom is slowing down. Also, the bottom, when it hits the bottom, it also pushes them up. This is why you look out. Yes?
Oh, George was here and I just thought I'd say hi.
Hi.
Great teacher. Great.
Yeah, tell the principal. But the water gets pushed out, pushed up. This is why you look out. It doesn't look like very wavy and thing, but you get toward the coast, it gets, the waves seem to be getting really big. It's because the ground basically pushes up. But it also slows the bottom down. Now let's think, if you were running along and something grabbed your ankles and stopped your feet, what would happen to you? You'd fall forward, right? Well, the same thing happens to the waves, is the bottom slows down, but the top doesn't, so they fall over. And they take that shape, which is the breaker. This is why the breakers are round, because the top is falling over. How far that is and where it is, again, depends on the bottom topography. Some beaches, they break out way out. You go like La Jolla. La Jolla, you can like walk out like 200 yards off the beach and you're like only in waist deep water. It's really shallow. It's a very shallow beach, very gentle waves. Some places, like if you come up here to Montana, the Montana beaches or some of the Sonoma Coast beaches, they basically are very steep, and sometimes they have something off the shore, and basically what happens is the wave comes in, all of a sudden, whoosh, wham, lands you and pulls you off the beach. These are called sneaker waves, sleeper waves, rogue waves, because you don't see them, and all of a sudden they come up, they break on top of you and pull you down. The trouble is they pull you down and kind of roll you down here in the bottom. You know, and this usually means lights out. This is why those beaches have these signs. If you look at the signs, they say, I mean, what they're saying is that, so in rough weather, you don't really do that. Someplace like Mavericks, they actually have pinnacles way out, about a mile offshore of these pinnacles, and that's where the water breaks. But that's why they get these big waves, because of the way that those pinnacles are. But they're a good ways offshore. I mean, the area for Mavericks is quite a ways offshore, like mile offshore is where they're actually surfing. Long way. And then they have the tournament when they get some of the big storms come in, and that's when they do that. Tsunami does the same thing. Now, you'll notice when this wave is coming in, it will pull back some of the water. And you can see that at the beach. Like the water goes out, and it comes back in. Because as this wave is building up, it's coming in, it's pulling water to it. And it's rotating like this, so it's pulling some of the water to it. And these are small waves, but a tsunami has an enormous thing, is huge. And it pulls out a lot of water from the beach. If you're out at the beach and all of a sudden the water starts receding, you run the other direction. Now that doesn't mean the tsunami is coming right away, because sometimes it depends on topography. It may take more time for it to recede out. But you want to get to high ground. If the water starts going away, you're running to high ground. Because when the water comes back, it's going to come back very, very fast. Think tsunami, the wave speed in tsunamis, well, the mid-ocean is like 700, 600 miles per hour. So this water comes back very fast. So when it does come back, it's going to be moving very fast, and it's it could be very loud. You saw some of the destruction that was there in Indonesia a few years ago. I mean, those were only, and really the tidal waves there were only like maybe 3 feet, 4 feet. That doesn't sound very much, but that's a lot of water. A lot of water on that. And I think that's it. That's it. Okay. So that's it for lecture day. So you need to write your summaries and all that stuff.